Okay, welcome back to the algorithm analysis slides. Let's keep on trucking and finish these up today, and we'll also start some new ones. So we know how to analyze stuff now. Let's talk about the different kinds of analyses we might want to do. So there's like three lenses that we look at that we look through potentially when we're analyzing something, when we're talking about its asymptotic complexity. Most cases, most time, we spend focused on the worst case. Okay, so we care most about the worst case. That's like when everything goes horribly wrong, like what is the running time of your algorithm? What is the space usage of your algorithm? When nothing goes your way and you take the most amount of time you could possibly have taken, the most amount of space you possibly could have taken. So this is what we try to teach you in this class in CSCI 41, so this is the one we want to get you good at right now, because that's like, if you make a better worst case, then your whole algorithm improves. But there's some other ways of thinking about your algorithms as well. You can always talk about it from the best cases perspective. That's like when everything goes right, and you take the least amount of time and space. And so like, what's the best my algorithm could do? Let's think about it positively for once. And then in the middle, you have the average case. That's like when you average together every possible way of your algorithm running on every possible input, like what happens, okay? And this is more suited for a fancier algorithms class that you're going to take when you get to a four-year college. So be on the lookout for average case analysis there. But we'll talk about it a little bit right now. We'll talk about it a tiny bit in this class. So yeah, let's take these ideas and bring them back to something we understand. Let's do it for binary search tree search operations. So here's an example binary search tree. It's got a root. There is the root of that tree. And let's think about the worst case running time, the best case running time, and the average case running time. Yeah? So, okay, what's the worst case running time for searching for something in a binary search tree? Well, it's pretty much like when you get, like you take the longest amount of time you could possibly take to search for your thing. So probably the best example of something that takes the longest is like when something's not there. Let's say you search for like 6.5 in this tree. See how you're going to go left, right, right, left, and like then you're not going to find it. That's where 6.5 would have been. But so that's kind of the worst case, right? It's the longest possible time it could take. I can think of an even worse case. What if your tree looked disgusting like this? It's like that one, that one, that one. It only had right children. Like you put everything in sorted order or something. So that's horrible, right? And let's say that like you were looking for something that wasn't there as well, like something bigger than the maximum thing. So again, you take, essentially, like you go down here and you wouldn't find the thing. You would take the size of the tree, the number of nodes in the tree, to figure out that the thing wasn't there. Does that make sense? So like, this is your worst case. The tree was a list, essentially a list functioning as a tree though, and the value that you're looking for, not there. See that? That's the worst it could be. Because like you're comparing against this node, it's not there. Comparing against this node, going right. This node, this node, this node. You're comparing against all n nodes in your tree, and you're noticing that, oh, you go right once more. It's essentially like, and then you have to check for null on the n+1th node that is null, right? So essentially you're doing like n+1 comparisons. And you're doing constant work at each node. So it's essentially n+1 things to do, and so it's theta of n. See, it's linear running time in the size of the nodes in the tree, in the very worst case, okay? If your tree's balanced, that's pretty nice. We'll talk about that in the average case. But you have no control. In the worst case, your tree like looks this ugly, and that's your running time. Okay, what about best case? What's the best your algorithm could do for searching for something in a binary search tree? Well, what if the value you wanted to search for was like the number 8? It's right at the root. You only have to compare one thing, right? So that would be constant time. It's never going to go your way this often, but in the best case, like you will find the thing immediately and it'll be there in constant amount of use of like searching, constant amount of comparisons, constant amount of running time. So that's fun. And then we can talk about average. All right. So in the average case, you have trees that look like this. You have a bunch of trees that look like this. You have a bunch of trees that look jumbled like this. On average, this is very hand wavy, but you'll talk about this more in an upper division algorithms class. But on average, a tree is kind of balanced, right? And so how long does it take to get to like the worst case for looking in a balanced tree is like the thing's not there again still. Like how many comparisons do you have to do? How many levels do you have to search through in a balanced tree to get to the last level and notice that the thing that you're looking for in the worst case wasn't there? Well, your tree becomes logarithmic in depth, right? It has a logarithmic depth relative to the number of nodes in the average case when it's balanced. Okay, does that make sense? So that becomes a log of n, average case running time for searching through a binary search tree. Okay, so those are like the 3 different flavors, and hopefully they make a little bit of sense. So we care most about worst case in this class though, but now you know. I might ask you about best case, maybe even an easy question about average case. Now you know how to think about it. Let's take some code that we've already written for our labs, and let's see what is their running time. Let's figure that out. So let's do is prime. We need that one. So let's think about the algorithm itself. Like, what does it mean to check for primality? So you could do like, it's essentially your is prime function. It's a loop, right? For I equals 2 to like essentially the number, right? The number -1 maybe, x -1. That's one way to do it. But the fancier way was to go up to, because you just were looking for one factor, just go up to the square root of the number you're trying to take, trying to see if it's prime or not. So that's the faster way. And then what you do is you check, right? Check if I divides x, because it's x that we're trying to see if it's prime or not, divides x. If it does, that means we found a factor that's not 1 or the number, so return false. If so, otherwise, let this whole loop play out, and if you don't find a factor, then you're good. You return true, it was a prime number. Okay? So essentially, the bulk of the work is going to be done in the body of this loop. And what are we doing inside of the loop? We're doing a comparison, right? Doing a modulus check. So it's constant work inside that loop, and how many times are we repeating it? Square root of x -1 times, kind of. Okay, does that make sense? So it's like a conditional and a return false. Like if you want to count basic operations, it's like, all right, 2 things being done in here times like the square root of x amount of times that we're doing it almost. Plus like a return true, essentially, something like that. All right. If you want to count basic operations, it kind of looks like that, but you don't have to really do that. Just notice that this is constant amount of work done in here, and we're multiplying that by square root of x. So this becomes the analysis, right? Plus that 1 to return true maybe would be, in the worst case, right? You're trying all these numbers, they don't work out. You're never returning false early. You're getting to this line. Okay, so essentially that's what's happening in the worst case. And so we're counting all those things, and it's theta of square root of x. That's an interesting algorithm. We never see square root come up a lot. But this is a square root running time algorithm. Okay, in the worst case. In the worst case, you got to run through this whole loop and then do the return true. So you got to do all square root of x iterations, essentially, plus that 1 to return. Okay, that's the idea. So hopefully that's making some sense. Let's do the rest of these. Let's do our calculate pi. So we threw a bunch of darts, and we tried to use that to calculate an approximation of pi. So what was that algorithm? It was a loop, right? Do num darts times, like the user told us how many darts to throw at this virtual dartboard. Do num darts times the following. Well, pick a random coordinate. Pick a random xy coordinate. Check if that coordinate was inside the unit circle, right? Because we're throwing unit circle things. Our dartboard is a radius 1 circle. Check if inside unit circle, that's my best drawing of a circle. And then if it is, add to the count, because we're counting how many did land inside. Add to count. If so, and then at the very end of this loop, once we're done, we have our statistics. We can take, we got to calculate and do a division, right? Got to do like the count divided by num darts, the number of darts we threw. That's going to divide the number of ones that landed inside. That gives you an approximation of pi over 4, but then you multiply that by 4, and you get your answer, okay? So let's analyze this. In the worst case, there is no best or worst case, honestly. It's the same amount, because you're always going to do this loop that many times, yeah? So like what is the running time of the body of this loop? Well, picking random numbers, that's constant. You can assume that the rand function is going to return things in constant time. A check with some square roots, some fancy stuff, but it's just a bunch of math. It's a constant amount of work to do per coordinate, and then adding the count if you need to. In the worst case, you do every time, right? That's going to be just like a plus plus operation. That's another constant time thing. So this body of this loop is constant time, all right? But it's multiplied num darts times. See that? And then this return statement is just doing some math. That's again constant. Okay. So the analysis then, in the worst case, and the best case, and the average case, because it's always num darts times, is like constant times num darts plus another constant. But the num darts wins out, right? Because that's the variable. Num darts. So it's essentially linear. It's linear in the number of darts to throw. Okay. It's just a long variable name this time. And then sat solve. That was the hardest one we've done so far, computational complexity-wise, at least. So if we sat solve a formula, we have to try every combination, right, of all the variables in that formula, all right? Like if there were 3 variables, x, y, and z in your formula, you had to try all the different combinations of true and false for them, like false, false, true, false, true, false, false, true, 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 false, false, all the options, right? All the way to true, true, true. How many options do you have? Let's say that you have n variables in your formula. You're essentially trying 2 to the n options, right? Because you have 2 options per variable. You gotta try everyone. And so for every option, we're generating all these options. What were we doing, right? We're generating all these options, and we're testing if this particular combination of true and false makes the formula true. And just going through the formula, that's essentially constant time because the formula never changes. So it's like you're doing this many times a check, right? Essentially a check, and we'll say that that's going to be constant time, all right? This is what's winning out, all right? The number of variables. N is the number of variables here. So our analysis then is, well, worst case, best case. It's all the same because we're trying all these options. Right, we got to try them all. So we're trying 2 to the n options and doing constant work at each option. So this is theta of 2 to the n. This is exponential complexity. This gets really big really fast. And so for formulas with a lot of variables, your program's not going to finish within your lifetime. It's crazy to think about that, but that's how it works. So yeah, these are just a bunch of examples of how I might think about analyzing these. I hope that helps you. And yeah, let's just imagine 2 to the n, that would take our lifetime, over a lifetime for large values of n. Let's think about that. So instructions inside of a computer, let's pretend that they take about a microsecond, 10 to the negative 6 seconds to execute just one basic instruction inside of your computer. That is more or less accurate these days. Gets slightly faster over time, but this is a good approximation. And then let's say that this is our analysis. We analyzed a function, and it has this running time, or this running time, or this running time. Let's see how long it takes in terms of clock time. If our input size is n, 10, 50, 100, 1,000, 10,000, and 100,000. Okay, so for logs, you're still in the microsecond range. It's like blink of an eye, very quick to do something. Okay, when your size of your input, when your running time is linear, then you do kind of feel it once n gets pretty large. I mean, you can see it, like humans can discern 0.1 seconds essentially. So that's noticeable now when n gets large. N log n, like your sorting algorithms, you can see that those are pretty still very fast for large amounts of values, but you have to wait. You have to wait. It's not instantaneous. Okay, and then n squared algorithms, that's like the edge of what is feasible these days with large inputs. So you can see as n gets larger, you have to wait a few minutes. When n gets pretty large, you have to start waiting on the order of hours. You double this again, even more. Soon it'll take a day to run an n squared algorithm on a couple million inputs. Yeah, so that's an issue. Interesting. And then n cubed, like cubic algorithms, you can see that it does not scale. You want to run that same amount that took a few hours for n squared algorithm with an n cubed algorithm. Now it's going to take, on input size of 100,000, it'll take a few years, right? A good chunk of your lifetime, if that's so. it really pays to like make the best version of the algorithm. If it's n cubed, try to make it n squared, because you see the time savings. You see that. It's crazy. And then exponential is just infeasible. Like, this is our sat solve formula. Exponential is as good as it really gets. You gotta try all those options. Once n becomes 50 variables in your formula, it takes like a third of your life, right, to finish the algorithm. Crazy. And it's just infeasible for any of these other ones. Okay, so crazy. So yeah, there's a fun story if you heard about it. The game Grand Theft Auto 5, they had an n squared algorithm that like kept them on the loading screen for a while. Like, a hacker discovered the issue, and like it could have been a linear algorithm, so the loading times became really bad for no good reason, and they eventually fixed the problem. If you want to go look into that, just search for n squared GTA 5. It's a problem. We would like to have the best algorithms for our purposes, and you can hopefully see why now. Okay, so yeah, before I give you a different topic, let's talk about just one last thing. Let me give you an example, a question to solve, and then I'll help you analyze it. All right, so here's a function. It's called maximum subsequence sum. It does a cool thing. Try out some options, see what it's doing. But I would like you to give an analysis of it. Characterize the asymptotic growth in the worst case for this algorithm. All right. But first, let's go over it, and we'll try some options, and then I want you to try the analysis. But we want worst case analysis. So here's what it does. So it goes through, like, it gets a sequence, like a vector, essentially a size n. You have the vector and the size at your disposal. Those are the input, and your output is the maximum subsequence sum. So let's say that we have our input as this sequence. Let's say it looks like this. We got 5 elements in our sequence. Let's say 1, -2, 3, 5, -7. So what this algorithm is going to do, it's going to try to find the longest chunk, contiguous chunk of this sequence, or let's pretend array or vector, that makes the biggest value, right? We want to find the biggest value of a contiguous chunk of this sequence. That's what a subsequence is. It's got to be contiguous, okay? So essentially, if you think about it, like, if you want to sum together all of this, it's not really nice, because that -7 is not helping us, right? So like, definitely don't include the -7 in your chunk. But now it's like 5 + 3 is 8, 9, 8, 7, right? So it's 7, but do you see that you could like change the chunk size? You can still find a contiguous chunk, and it would be better, right? So like, this would be the maximum subsequence sum right here. It would be the 5 plus the 3. See how that's the best chunk, the best contiguous chunk of this array that adds up to the maximum value. Because if you extend this in any direction, it's not going to help you, right? This becomes 6 now. So like, this is the best chunk, these two. This is the subsequence, and their sum is 8. You see that? And we want the maximum subsequence sum. That's what it's doing. So yeah, you're getting a sequence, you're getting the length of it, and this is how it's computing it. All right, it's going through for I equals 1 to n. It's going through all the indices. Indices start at 1 in this pseudocode. It's a little weird, I know. And then it's like saving max sum, our current sum of stuff it's going through. Okay, and like it's going to be a nested loop. See that? So see if you can analyze that now, and then I'll give you my analysis now that you know what it's doing. All right, so we want worst case, and so let's think about this. We've got, well, we've got for I equals 1 to n. What's it doing? Well, that's going to iterate. We know it's going to iterate I times, right? It's going to iterate exactly I times, and okay, then it's going to repeat this line, for example, then I times. For sure, or sorry, n times. Sorry, it's going to repeat n times. Sorry, for I goes from 1 to n. So this line is getting repeated n times. It's constant complexity for this line, so that's like O of n that contributes. So this is constant for this one line. And then we have another loop for j equals I to n. Interesting. So it's like getting shorter. Like when I is 1, it goes from 1 to n. When I is 2, it goes from 2 to n, and 3 to n, 4 to n. So it's like doing less work as I gets bigger. That's interesting. I'll have to consider that. But then it's doing this, like it's doing its body. So what's it doing in the body? It's doing an addition, an assignment, a comparison, and another assignment. So this is all constant work. In the body, it's just all a bunch of constant stuff, so the whole body is constant. And then, like, we're done with this loop, and then we return our things. Okay, so, okay. That's that. Now we need to figure out the analysis, right? Because essentially, like how much is this executing? That's a little weird to think about. So like it's doing all this stuff. This is constant work in the body, but it's running this body a weird number of times. And like this guy is, it's constant, but it's being repeated n times, right? So whatever this is, it's also being repeated n times. Just a weird way of doing things, all right? So this for loop is doing stuff n times. And so this line right here, in total, how many times is it running n times? How much work is it doing then? Linear work for this one line. I'll put it in rainbow, okay? And so our goal is to figure out what in the world is going on right here. How much work is being done in total by this thing, okay? So our question to ask ourselves is, how many times is this inner loop body running, really? Because it's doing constant work, but how many times? How many times? It's weird to think about. All right, so, well, let's figure this out. When I is 1, this whole loop, how many times is it running? It's going from 1 to n again. So if I is 1, it's going from 1 to n when I is 1. All right, so if I equals 1, then the inner loop iterates n times. Okay, I hope you see that. And then when I is 2, then j goes from 2 to n. So if I is 2, for a similar argument, for a similar reason, it goes n minus 1 times. It iterates its body n minus 1 times. When I is 3, see the pattern? It's going to iterate its body. It's going to run it n minus 2 times. Okay? That's how that's working. And so, in essence, this body of this inner loop is getting run n times plus n minus 1 times plus n minus 2 times all the way until n times plus n minus 1 times plus n minus 2 times all the way to what? Do you see it? All the way to when I is n, and so it's n to n, so it's just one time, okay? Just one time. All the way down to just 1. And so if we really want to be precise about this, we have to figure out, because what's it doing for each of these loops? It's doing constant work n times, constant work n minus 1 times. So really, if we can solve this, that is the running time. See that? Because it's just multiplied by a constant for each loop body. This is how many times it's running the loop body, and we're doing constant work inside of that. So it's perfect, all right? So that's essentially how many times this is being run. That's the analysis of this one. And there is a closed form for this. Have you seen it? If you do the sum of all the numbers from 1 to n, there is a formula for that. It's n plus 1. It's like, wait, the trick is, right, to add it to itself backwards. It's n plus 1 n times over 2, because you double counted. And this expands, right? You can expand that to be, this is like n squared plus n, all of that over 2. So it's 1/2 n squared plus 1/2 n. What's the analysis of this, right? N squared is the biggest. This is a constant. So this becomes theta of n squared running time for this. Right? All of this loop, we counted how many times it's running its body, how much work it's doing. In total, this loop is doing theta of n squared still. Okay? So that's the idea. So when you see an inner loop that kind of goes a little less every time, it's still like multiplied by this, and it's still n squared. You can think about it that way, but now you know why. So this line contributing linear time, this line, all this entire inner loop contributing n squared work, and then this this last return statement is going to be just constant, right? Constant work to return something. So that's all good, all well and done. And so essentially we're just adding up every line doing stuff. This was also constant time to run this, just initialize the variable. So it's constant plus linear plus n squared plus constant. See that? So that is your analysis. And so in sum, finally, what wins out? What's the analysis of this whole thing? It is a theta of n squared running time. All right. And now you know like how much time it's going to take for different things. But that is maximum subsequent sum. Even if you didn't know exactly what it was doing, you could still come up with this. Just like looking at how many times is this loop run in its body, like in total, how much stuff is being done. Okay, so it's this inner loop That's kind of the bottleneck. It's being run that many times, and you're doing constant work that many times. Okay, so that's the beauty of it. That's how you solve that kind of stuff. That was the worst case, essentially, and the best case, because it's like n is always there, and the average case. You got to try them all, so they're all the same. So that's my analysis of this algorithm. Hopefully it makes a little bit of sense and you got close. If not, you got it perfectly. Okay, so let's move on to the last topic for these slides. Let's talk about something called finite state machines, which are very cool, very powerful. If you can get your program to look like this, finite state machines are an easy way to make it correct. All right, so here's what a finite state machine is. It's just a model of like computation, very abstract. It has a bunch of states, circles, and arrows. It has a bunch of states and transitions between those states after taking input. All right, so here is, every circle is a state. So even and odd are a state. And then inputs are along these lines. Like if you see an input, it will drive the state and move it to, like, it'll keep it in even. Or if you see a 1, it'll move it to odd. Or if you were in odd and you see a 1, you'll keep it in odd. If you see another 0, now you're in even. Okay, so it's like circles and arrows. It's transitioning. Potentially there might be output as well. That's what this one is showing. But finite state machines, FSMs for short, they have a start state. They have to have a start state. It's like you got to pick which of the circles you start at when you run this algorithm. So that the arrow coming in from nowhere is your starting state. So even is a starting state. And may optionally have final states or accepting states. That's a double circle. So apparently this finite state machine really wants to end in the even state. That's its ending state, final accepting states. Okay, so it's accepting things. This example on the right, this first one, is a finite state machine that accepts even binary numbers inputted as strings of 1s and 0s. All right, do you see that? I'll prove that to you right now. So this one, if you feed it the binary string, let me go back to a different color, sorry. If you feed it the binary string, let's see, 0, 1, 0, you know that's 2 in binary, right? So this is the number 2. What you do is you feed it in an order, so you're going to like feed in, you're starting in the even state, by the way. You feed in the number 0, so you start here, you ran it on the 0, so you're still in even. See how it's working? Then you feed it the 1, you were in even, you gave it a 1, now you're in the odd state. And then you're in the odd state, you feed it a 0, it gets that 0, it follows this transition back to the even state. Okay? So that's where you end up, and it accepts the string because it was an even string. So like if you put another 1, that would bring you back to an odd number because odd numbers end with a 1 in binary notation. So this is accepted because we ended in this state. All right, we started in even, we ended in even. I hope that makes sense. That's how that one works. And yeah, I think that's what I wanted to say. Just like also just the number 0 even. The number 0, you don't do anything, right? It's just the string 0 in binary. That's equal to the number 0 in decimal, of course, right? That's the same. You feed it in the 0, and it's like, oh yeah, 0 is even, and it stays and it's happy. This is in the even state. But like 1, 1, what's that? That's equal to or equivalent to 3 in decimal. That's an odd number. So 1, 1, starting here, feed it the 1, you're in odd. Feed it the 1 again, you're still in odd. This is a state. This is a string that's not accepted by the finite state machine. But if you add another 0, right? Because you were 1, 1. If you add another 0, that makes it, now it's 6, right? Adding a 0 multiplies by 2. So you were here. You added that 0. You're back in even. Now you're accepted again. See that? That's the idea. So 0 is also even. 0 is equivalent to 0 in decimal as well. All right, so hopefully that's making some sense. So like you feed it an input, and it tells you where you are, and it like can take some things. This is a finite state machine that makes sure it's only given even things, even numbers. That's pretty cool and powerful. All right. Potentially, you can also have output. You can output something every time you transition. So like this is how you draw that. So like here's the starting state, and this is like an old-timey vending machine that took nickels instead of quarters, for example. So like this takes a nickel, like the input, and then there's a slash, and then here's an output, optional output. That's how you read it. So like you feed this, what's it called? You feed this vending machine a nickel, that was your input. It'll take you to this state and output nothing. Then you feed it another nickel, takes you to this state, outputs nothing. feed it a couple more nickels though, then it will return you your prize, whatever you were putting into this vending machine. Okay. So eventually it will produce an output on one last nickel input. See that? So that's the idea. And apparently it keeps giving you stuff every time you put in another nickel. That's pretty funny. Or maybe it goes back to the state. Who knows? Depends on how you program it. But hopefully that makes sense. So like this, that's how you notate that. Like this is your input. Then you put a slash. These are your inputs, and then these are your outputs. So that's what it means to be a finite state machine. So like you feed it in stuff, eventually like it's keeping track that it has like 20 cents in it now. And I guess you put in one more nickel, now it has 25 cents, and it gives you back. It finally returns you something. It was waiting, returning nothing until then. Okay? So that's the idea. Those are finite state machines. And these are very powerful. Like I hope you can see how cool it is to like have a very simple mathematical thing with arrows and circles that like tells you when a number is even, like it accepts only those numbers. It's very cool. Here is mathematically how you define what it means to be a finite state machine, the technical definition. It's 5 different things, right? So it's a finite state machine. If you want to define it formally, it's a 5 tuple. You need these 5 things to define a finite state machine. We're going to call those things big Q, little q naught, I, A, and delta, the Greek letter delta. So lowercase delta, that is. So what finite state machines need, they might also need, actually, if you produce output in your finite state machine, they need a set of outputs as well, instead of A, maybe. Sometimes they do that, so it still could be a 5 tuple. But sometimes there are accepting states and outputs, who knows? So you might need extra things, but there is a concept of a transition function, and that will need to give you back something in addition to taking you somewhere else. So I'm about to explain this. But let's formally specify our even bit string finite state machine, so this one. So here's what a finite state machine needs to define it. You need a set of which states are in the machine. So that's Q, that's your set of states, it's finite. It's a finite state machine, yeah. And then Q0 better be one of your states, that's your start state. You always need a start state, you need to know where this machine begins its life. Then I stands for input actions, it's things that you can feed into the machine. So we're feeding in 1s and 0s, so our input actions are either a 0 or a 1. All right, for this particular state machine, but that's like what it takes. That's the valid things you can give to it that it will like move around in the machine with. And then you need a subset. We're going to call that A for accepting states. Accepting states are a subset of your total number of states. Like your total states are even and odd, but we care about even ones. So our accepting state is just the subset containing only the even state. All right, I'll draw that in a second. So it's a subset. And then your transition function is how you move around. It's like given your current state and a new input, where do you go? What's your output? It's like given that you're in the even state and you see a 0, you stay in the even state. Given that you're in the even state, you see a 1, you transition to the odd state. All right, so hopefully that's making some sense. But yeah, let me take this as just a picture so that we can see it. It'll be a little small though. I'll put it here, very, very small somewhere, maybe there. And let's figure this out together, okay? So our set of states, Q, looks like this. Q is just our 2 states, even and odd. So those are our 2 states. That's a bad looking Q. That's another bad looking Q. I'm happier with that one, I guess. So Q is even and odd. Those are our 2 states in our finite state machine. And then our starting state, Q naught, Q0, that is the even state. That's what we'll define it as. Our input actions, the things that we feed in to drive our finite state machine, are either 0s or 1s. Those are the things on the arrows. So I is either we see a 0 or we see a 1. Those are our input things that we care about. Our accepting states is a subset of our total states. We care about things being even. So the state of places that I want this machine to end on, the set of states that I care about this ending on, is just the set with even in it. That's all I care about. And then finally, the transition function. So here's delta, our transition function. I'm not the best at writing a Greek delta. That's kind of good. All right. What does this look like? There. This is equal to, well, what do we got? Well, what is a function but a set of input-output pairs? So if you see, if your state is even, and you see a 0, you better output, you better stay in even. See that? That's your result, even. That's how you can define a function, just as a set of pairs, inputs and outputs. All right, and then if your state was even and you saw a 1, what do you got to do? You're going to go follow that transition and you're going to go to the odd state. See how this is representing exactly what the drawing is saying. You're going to move to the odd state. You're going to transition to the odd state. And then finally, if we're in the odd state and we see a 0, we got to move back to the even state, because that now ends in a 0. It's a now a multiple of 2. So now we're back in the even state. And then if we were in the odd state and we see a 1, then we better remain in the odd state. So we're still odd. Odd, see a 1, still odd. So that's how we stay. So these are the 5 things you need to define exactly what it means to be a finite state machine. So everything in the picture is represented in these 5 things. All right. So yeah, that's the full transition function as well. And so that's the idea. I don't know, maybe that's a prettier delta. So yeah, that's what it means to be a finite state machine. Now you try. So I would like you to run these 2 finite state machines. Here's 2 of them. Stole them from your book. So here's finite state machine 1, finite state machine 2. I'd like you to run each of them. They take binary numbers. Run them on each of these strings. All right, starting from the start state for each of them. Okay. So like for finite state machine 1, tell me what this string is going to produce. What state are you going to end on? For finite state machine 2, for the same string, tell me what it's going to end on. Do it for all of them, please. Right? Indicate which state you're on at the end of the string, and then tell me if it was an accepting state or not. Remember that the double ones, these are accepting states. So, all right, you try that. Okay, we got 1, 0, 0, 0, 1, 1. So starting here, 1, 0, 0, 0, 1, 1. So that means we end on B for this one, and that is not an accepting state, sadly. Only C is an accepting state, but we ended on B, so that's not accepting. And then finite state machine 2, we have, again starting here, 1, 0, 0, 0, 1, 1. So we end on A. And ooh, that one is an accepting state. Nice. And then let's try these other ones. I'll do them more quickly. So we have 4 zeros. 1, 2, 3, 4. That's D for that one. And then 1, 2, 3, 4 for that one is A. D is not accepting, but A is accepting. Cool. Nice. Then we have this one, 0, 0, 1, 0. 0, 0, 1, 0, because we're kind of like, it's never going to work if our first thing is a 0. It's kind of keeping track of that. So on D again, sadly, which is not accepting. And then finite state machine 2 on 0, 0, 1, 0. 0, 0, 1, 0. We're ending on C this time. But that's not accepting. Only A was accepting for finite state machine 2. Then we have 1, 1, 0, 0 for this one. Is it happy? Is it finally happy? 1, 1, 0, 0. Hey, there we are. We are in C, and that's an accepting state. Awesome. And then what about this one? We have 1, 1, 0, 0. That's going to take us to D, which is sadly not accepting. Interesting. So that's what's going on for those 2 finite state machines, and I hope that made sense. Okay, so that's that piece. Let's move on now to a new set of slides. We only have a few of them, but I'm going to teach you a new topic today. We're going to get started on it. The topic is called induction and recursion. This may be the most important set of slides for this class, arguably. So this is going to take us a few lectures to get through. It's very, very cool. Induction is very, very powerful. It goes hand in hand with recursion, which is something you're going to get very good at, hopefully, by the end of this class. So, all right, let's start with a topic that is familiar, hopefully, from math class. Let's talk about sequences, all right? So a sequence is just a bunch of numbers in order. Like this is a sequence. 1, 2, 3, 4, 5. That's a sequence of just all the numbers. You can have a sequence of 2, 4, 6, 8. You can have a sequence of 2, 4, 8, 16, 32, blah, blah, blah. So sequences are just numbers in order, but how can you represent them inside of math? Well, you can represent it as a function who takes integers to some output. So it's a domain where the set is some set of contiguous consecutive integers. All right. So that's all you need. It's just a function. You can define a sequence as a function of consecutive integers. So for example, here's the Fibonacci numbers. You've seen the Fibonacci sequence before, hopefully. Let's say that they start at 0. The first two Fibonacci numbers are 0 and 1. And then you know to get to the next one, it's like the other ones, you add them together, and that gives you the next one. So 0 plus 1 is 1. 1 plus 1 makes 2. 1 plus 2 makes 3. That's the next term in the sequence. 2 plus 3 is 5. 3 plus 5 is 8. Yeah. So that's the Fibonacci sequence. It's an infinite sequence, but like this is the 0th term of this is the first term, the second term, third term. Each piece is called a term, by the way, and the I is called an index. All right. So you can make this a function. It's like, all right, what's the domain of the function? Well, it's like, what are the pieces? Like you can ask for the 0th thing in the sequence, the 1th thing, the 2nd thing, 3rd thing, 4th thing. So the domain is going to be these numbers, right? So this is domain of the sequence. You can think of it as a function. It's like 0. You can ask for that element of the sequence, element 1, element 2, element 3 of the sequence, 4, 5, 6. You can ask for all of those. And then you can define, like, give your function 0. That's asking for the 0th element of the sequence. Like the answer, this maps to 0. This maps to 1. F of 2 is 1, right? So this is going to map to 1 as well. And then this will map to 2, this 4 will map to 3, 5 will map to 5, and then 6 will map to, 6, it'll map to 5 plus 3 or 8, okay? And then that, of course, goes on until the end of time. So that's what it means to be a sequence. So every piece of the sequence is called a term, like this is the term number 3 of the Fibonacci sequence is 2. So this is the term at index 3, you can also say, is 2. So I is also called the index. Maybe that's where we got that word from for our loops. So, or for our arrays and things. So this is the 3rd term of the sequence of the Fibonacci sequence. It's at index 2. All right. And yeah, you can start defining them these ways. You can be like, all right, the 0th term of our Fibonacci sequence f is 0, or you can be like, let's make a function that defines the sequence. Just give me which term you want. I'll give you out which one is at that index. Okay, so that's sequences in a nutshell. It's probably more complicated than it needs to be. It's like that's how precise we have to be in math. And the Fibonacci sequence, by the way, is really well found in nature. It's very fancy, and it's like has to do with the spirals on like snail shells and things. But you can look at that Wikipedia page if you'd like. It's very cool. Leads to the golden ratio, apparently. Very natural things, like all of nature has the Fibonacci sequence in it. But let's continue with our ideas of sequences. So let's have some more definitions, of course. We say that a sequence is increasing if it gets bigger, right? So here's how you define that in math. So if for every 2 consecutive indices of that sequence, k and k plus 1, then the values at those indices better be like this. This better be their relationship for any possible k, right? The one after better be bigger than the one before, right? That means it's increasing. I hope that makes sense. So this is here's an example. Like you have your 2 indices, k and k plus 1. This should be always true for every piece of those. So here's an example, of course, of an increasing sequence. 0, 1, 42, 43, 55, ... So that's an example increasing sequence. And the idea is like you're looking at every pair. Like you're taking these guys, looking at each of them. Then you're looking at these ones, these ones, these ones. This should always be true for them. All right? It's like, this is what the definition means. Like zoom in, and everybody gets a chance. Zoom in on your sequence. Like look at these values, 42 and 44 maybe this time. You're going to look at each of these and make sure there's your sequence A of k. Here's your element A, k plus 1. You're going to make sure that one's bigger than the other, right? That's what it means to be increasing. You're going to try all of them. Everybody gets a chance. You're going to compare those guys, compare these guys. You can compare even these guys as well. They all get a chance, okay? Onwards, each way. So that's increasing. Another term is non-decreasing, which sounds like the same as increasing, right? But a sequence is non-decreasing if the only change is the less than or equal to rather than the less than. So it can stutter. It can stay there for a certain amount of time. So like this is a non-decreasing sequence. Like if you compare consecutive elements, then consecutive terms, I guess, then this holds for each of them. The one after is greater than or equal to the one before. And so this is an example of a non-decreasing sequence. Like you can have 0, you can have 0 twice. You can have 1 a couple times. It can stay there for a little bit. 4, 4, 4, 42. Doesn't have to stay on things. 43, that's fine. Still greater than or equal to, right? So that's a non-decreasing sequence. And this is actually what it means to be sorted, right? This is the definition of sortedness. Your array has elements in a non-decreasing order, okay? A decreasing sequence is exactly what you would expect. Things are getting smaller. The bigger indices are smaller if you compare, okay? So this is a decreasing sequence, like 4, 2, -1. I guess it could be +1. I don't know why I wrote +1 last semester, but let's keep it that. 1, -17, -42. You have to get smaller every time. Can't stay the same. All right, but I think you understand what non-increasing means now. It means you're staying the same or getting smaller. All right, 2, 2, 2, 1, -17 again, da da da. Okay, so that's going to be your greater than or equal to. Yeah, when you're comparing consecutive elements. So that's sequences. That's how you can describe sequences. And this is all going to lead to a concept of induction, mathematical induction. And it has to do with sequences deep down, so that's why we're learning about them here. But what mathematical induction is, or induction for short, is about, is it's kind of like you're building up some dominoes, an infinite chain of dominoes. And it's really, really powerful. Induction is a very powerful proof technique, maybe the most powerful one that we're going to use in computer science. So here's how induction works, and I'll tell you more about it next time. But here's the setup. Here's the hand-wavy idea. Pretend you have maybe an infinite amount of dominoes lined up. Hopefully you've played with those before. So you got a line of dominoes, maybe infinitely many. That's fine. And assume that you can prove the following two things about your little line of dominoes, potentially infinitely long. You can prove that the first domino is going to fall, and then you can also prove that any consecutive dominoes will fall. So if one domino falls, then the next one's also going to fall right after it. You know that they're not too far apart. It's always going to work. If one domino falls, the one after it's definitely going to fall. What is that? If you can prove both of these two things separately, what does that tell you about all of the dominoes at once? Can you see it? If you know that this one's going to fall, and then if that one falls, well, then the next one's going to fall. So you know that, well, this one's going to fall because you said so. And then you can prove then that this one that comes after it by thing 2, that one's going to fall. And then now if you know that this one falls, you know that the one after that one's going to fall by proof number 2, right? Then you know that this one falls. And then now that this one falls, you know that the one after it falls by the same argument. You know that all of them are going to fall. See that? You can prove with these two ideas that every domino must fall. Every domino will fall. And so if you had an infinite chain of dominoes, do you see how proving two things proves something about an infinite amount of things? It's very weird, very cool, very powerful. And that's our first taste of induction. But that's where I want to stop for the day. So I will see you back here, and we'll continue with this idea of dominoes falling infinitely many times forever.